Okay, so part 186 is line 18a4d Aneutronic fusion plasma alpha particle deuterium tritium HE3 PB11 5G Wow Seti. Again, with the 5G, that usually means something that can be used towards the fuel or the formulas for the jets, okay? So this is the alien radio signal here. And this is a graph here I found. CH2 boron composite target, high contrast 1011, chirped pulse amplification CPA picosecond laser pulse, accelerated protons yield P11 minus B reaction, resultant A particles 8.7 MeV. Okay. In Chapman's aeronautic fusion reactor scheme, a commercially available benchtop laser starts the reaction. A beam with energy on the order of 2 times 10 to 18 watts per square centimeter, pulse frequencies up to 75 megahertz and wavelengths between 1 and 10 micrometers, is aimed at a 2-layer 20 centimeter diameter target. So this is at the nextbigfuture.com website. And IO4A6 is an advanced fusion reactor for space propulsion and power systems from J.J. Chapman Engineering Division in NASA, Hampton, Virginia, United States. Recent progress on laser plasma accelerators and applications for compact, high-quality particle beam and radiation sources from 2010. Again, these are PDFs. I didn't want to download the PDFs. I just took the titles, okay? So this is how laser pulse traveling through a plasma accelerates free electrons in its wake. Again, this is part of the technology for the engine. We've been talking about using plasma, neutrinos, liquid argon gas, and I guess this has something to do with that because that's what it looks like. So we have the Berkeley lab scientists are leading in a race to develop laser-based accelerator capable of zapping electron beams to energies exceeding 10 GeV in a distance of just 1 meter. And here's the student here in the picture. This group achieved a major breakthrough in 2006 when they broke the world record for laser wake field acceleration, a technique in which particles are accelerated by waves in plasma generated by intense pulses of laser light. In the wake of the laser pulse, electrons surf the waves of the ionized gas. Lehmans and co-workers used this concept to accelerate electron beams to energies of more than 1 GeV in a distance of just 3.3 centimeters. Compare that to the Stanford Linear Acceleration Center, or SLAC, which takes 2 miles, 3.2 kilometers, to boost electrons to 50 GeV. Although the main purpose of the project is to develop a new generation of more compact accelerators for high-energy physics research, laser plasma wake field technology has several potential applications. So it shows the electrons and the positrons there and the type of force that they create. 100 to 10 GeV accelerators could enable a 100-meter long teravolt accelerator. And this is a concept of a tabletop soft X-ray fail. Okay. And a multi-GeV beam could be used to produce highly collimated, high-energy photons that could penetrate cargo in a non-destructive way, allowing inspectors to remotely see inside a package. So this is talking about some sort of X-ray thing, which would be highly useful for national security. Bella could also be used to build free electron lasers, FEL. Like all lasers, FELs emit energetic beams of light, but unlike conventional lasers, they operate on a different set of principles that make them highly tunable. Because of this property, free electron lasers can provide extraordinarily valuable tools for materials scientists, chemists, biologists, and research in various fields working on problems in fundamental energy research. See this little bug? He just likes to go around and fly in my face constantly. It gets into my water and in my food, so he's gone. Sorry. In various fields working on problems in fundamental energy research, allowing them to probe ultra-short nanoscale phenomena. Their tunability also makes them useful for medical diagnosis. Finally, with some modification, Bella could produce a narrow bandwidth X-ray beam. Oh, there we go. We need a narrow X-ray beam, don't we, for our engine. That could be used to take very high resolution X-ray images for medical use. Or you could use it for a UFO engine if you figure out how to do it. So if the laser technology that drives the laser plasma accelerators, See, we need laser plasma accelerators. So we need a laser plasma accelerator for our fuel. Keeps on improving by becoming less expensive and more compact. It could one day be an alternative to conventional X-ray machines, offering a new technique for better images with reduced X-ray dose. From what I've seen in the data so far, stuff that you guys created, say 10, 20 years ago for one thing, like the medical industry, you're finding out that those things can be used to power jet engines 20 years later. And on many of the times when we come up with the concept of, oh, we can use this for this, people say, oh no, that's impossible. But the actual is, if it's coming up in this wow signal data, then it means they're trying to tell you you can use it for your power, for your engine. You just have to figure out how. Okay? So, completing Bella will require one HC1W PW laser, the highest average power 40W petawatt class laser in the world. To achieve Bella's main objective of 10 GeV electrons, I believe Bella has already been built. This is probably old news. I have found stuff from Bella, so obviously they did make it. They did make it. I'm not sure if it's the exact same Bella, but I'm assuming it is. Main objective of 10 GeV electrons, a new and much more powerful laser will have to be put in place, a state-of-the-art laser that can fire a 40 joule pulse in a brief 40 femtoseconds. Now, the word joule came up in the 60QUJ5 alien radio signal, so that's a keyword there. And pulse is another keyword, too. Then build up to fire again and again, once every second, a repetition rate of 1 Hertz. Such a laser will have an average power of 40 W and a peak power of a quadrillion watts, a petawatt, 1 PW. Since the time we designed and built the Loasis 40 TW laser ourselves, there's been a revolution in the field of laser technology. Lehman says advances are now driven by commercial companies and by military requirements, and we have been talking with 2 companies who want to build a laser for Bella under our supervision. So again, it's plasma acceleration at Wiki. Planetary resources. This is the next thing that comes up. This is a graph about Fusion Ship 2. Dimensions are much larger than for a Saturn rocket. Remember that Fusion Ship 2 is a much more demanding Jupiter round trip. I shall make this a little bit bigger for you so you can see what it looks like. Just a tad bigger. There. Looks like 3 different types of ships there. Space shuttle. Ha! Look how small the space shuttle is compared to these monsters. Wow. Okay, this system will have 10 times the propulsive thrust of a George Miley IEC fusion propulsion proposal. 5 weeks to Mars with helium-3 version of the fusion spaceship. So they're talking about helium-3, and they're saying it only would take them 5 weeks to get to Mars with this helium-3 version. Whereas right now the Mars 500 is actually saying it's going to take them 17 months to get there with what they currently have. And what I was trying to do is get there in 2 months with my formula, but this is even better. But they said helium-3 is extremely expensive, so if there's a way of making a different type of fuel and mixing with something like the helium-3 plus the stuff we come up with, maybe we can get there even sooner than 5 weeks. That'd be cool, eh? 3 days. My ultimate goal is to get to Mars in 3 days, because that's how long it takes UFOs to go from Earth to Mars. If you look at the different sightings and stuff for UFOs that have been spotted from people, it only took them 3 days to get from Earth to Mars. I don't have the proof in this video, but it is in another video, okay? So if you look under UFO sightings with the Wow Seti videos, you'll be able to see it there. So this is IEC power units can be added in series to develop higher power units such as required for deep space propulsion. Magnetically channeled spherical array MCSA. High power operation eliminates grid structure, increased energy confinement time. They are tuning the IEC configuration for space propulsion. If they pulse it up to several thousand amps, then it is okay if IEC only has scales by cubing the power instead of up to the 5th power to get to 25 megawatts. Here's another paper that's a PDF file. It's at fsl.ne.uiuc.edu, and it's magnetically channeled SIEC array MCSA fusion device for interplanetary missions. They are modifying current IEC designs to increase plasma flow and pressure. They are also developing a novel form of air-breathing hypersonic spaceplane with an IEC. This is called air-breathing MHD IEC hybrid. The other is an injection of IEC with a unique device to enable a vehicle to do a horizontal liftoff and then proceed to LEO. By using these two technologies, we can develop a highly efficient single-stage to orbit vehicle that can operate both within and outside of the atmosphere. It can lift off from Earth, land on the moon, and come back without jettisoning any stages or equipment. And that's our goal too. This work is beyond the theoretical and is now solidly in the realm of applied practical science. Proton boron 11, the ideal fusion fuel, is helium-3, which is found in abundance on the moon. PB11 is nearly as good and requires minimal shielding from radiation, so we will initially use PB11 and switch to HE3 when it becomes available. Imagine a 500 metric ton spacecraft outfitted with a certain number of IE fusion propulsion devices. With PB11 fuel, it could lift off from Earth and reach Mars in 8 weeks or less. Using HE3 fuel, it could get to Mars in only 5 weeks. These reactors would be small enough to be placed on a spacecraft the size of a standard commercial jet. So, next thing is the aeronautic fusion quote from Wikipedia. I looked it up to see what it meant. So it's any form of fusion power where neutrons carry no more than 1% of the total released energy. The most studied fusion reactions release up to 80% of their energy in neutrons. Successful aneutronic fusion would greatly reduce problems associated with neutron radiation such as ionizing damage, neutron activation, and requirements for biological shielding, remote handling, and safety. Some proponents also see a potential for dramatic cost reductions by converting energy directly to electricity. However, the conditions required to harness aneutronic fusion are much more extreme than those required for the conventional Deuterium Tritium HE3 fuel cycle. The next two reactions rates involving P3He and 6Li, which is lithium, are not particularly high in a thermoplasma. When treated as a chain, however, they offer the possibility of enhanced reactivity due to a non-thermal distribution. So again, we're coming up with the plasma idea. They've got helium-3 and lithium-6, and both of these, helium and lithium, did come up in other formulas from videos 170 to 180. Those videos have all the formulas for fuel in them, okay? Fuel ideas, and there's like a lot of stuff there. The product 3He from the first reaction could participate in the second reaction before thermalizing, and the product P from the second reaction could participate in the first reaction before thermalizing. Actually, sorry, I'm going to reiterate that. The videos from 170 up to 215 now are in relation to the UFO engine, formulas, and math equations needed to create faster jet propulsions. Okay. There's also inventions and patents and stuff that you'll need to use for your components. So it could participate in the first reaction from before thermalizing. Unfortunately, detailed analysis do not show sufficient reactivity enhancements to overcome the inherently low cross-section. The pure 3He reaction suffers from a fuel availability problem. 3He occurs in only minuscule amounts naturally on Earth, so it would either have to be bred from neutron reactions, counteracting the potential advantage of aneutronic fusion, or mined from extraterrestrial sources, which they're thinking of going to the moon to do. The top several meters of the surface of the moon is relatively rich in 3He, on the order of 0.01 parts per million by weight. By mining this resource and returning it to Earth would be very difficult and expensive. 3He could in principle be recovered from the atmosphere of the gas giant planets Jupiter, Saturn, Neptune, and Uranus, but this would be even more challenging. The P-7Li reaction has no advantage over P-11b, given its somewhat lower cross-section. For the above reasons, most studies of aneutronic fusion concentrate on the reaction of P-11b. Okay, so the next thing is tri-alpha particle. Now, I don't know if I've got that wrong. I think it's just alpha particle. I might have did a boo-boo there. I'm not sure. So here's the A alpha particle equals He4/2. Plutonium-239 decays by alpha particle emissions as follows: Pu-239-94, 24,000 years, U-235-92 plus He4/2 alpha particle. That's the end of that video. We'll go into the next one now.